Okay, welcome back, and today we're going to talk about hypothesis testing involving a single variance or standard deviation. So let me set up the hypotheses. So again, we should be very familiar with the 7 steps. So this will go much quicker than the other chapters because I'm assuming that you already know how to do the 7 steps. It's just going to be setting up the hypotheses and then doing the correct test. And it's going to be a chi-squared test. But we're going to have to, in this case, there's no test on your function, on your calculator to do it. So we're going to have to use either the traditional method or the p-value method and use the calculator functions to get us those numbers. Okay, so watch and pay attention. Okay, so now we're going to use this formula for our chi-squared statistic, as we talked about before. So we're going to call our chi-squared star value, this is going to be our test statistic. It's going to be calculated by using the formula n minus 1 times our sample variance divided by the population variance. Now, this population variance is going to be what we're going to assume it is under the null hypothesis, okay? So this is going to be our test statistic that we're formula. Once we have our test statistic, then we can compare this with either a chi-squared L or a chi-squared R value, depending on whether it's a right tail, left tail, or maybe even a two-tail test. So these tests can be either one of those 3, left tail, right tail, or two-tail. Once we have the correct critical value, then we can use the traditional method like we always have. Okay, and like we learned before. Or you could take your test statistic and then find the p-value. Now the p-value is going to be using a new function on your calculator, which is called the chi-squared CDF function. Okay, so you can use chi-squared CDF, and just like your normal CDF function, all you have to do, or more or less like the TCDF, put in the lower bound, upper bound, and your degrees of freedom. Okay, so you're going to put in upper bound, lower bound, and degrees of freedom. And then that will give you your p-value. Now be careful, again, actually what this gives you is the probability, right? So it's the probability of being as extreme or more extreme than your test statistic, right? Okay, and then depending on if it's a left tail or right tail test, determines what direction your inequality faces, right? And then if it's a two-tailed test, you got to take this value and double it, okay? Now, in this case, we don't have a chi-squared test function for these. So you're going to have to do either one of these methods, either the traditional method or the chi-squared method, the way I'm going to show you. Okay? So now, let's do an example. Or actually, before we do an example, let me show you the sets of hypotheses. So here are the 3 pairs of hypotheses you could have. So we could have this one. So these are the things that we're testing. I'm going to put all of the hypotheses in terms of variance, but realize I can rewrite all of these in terms of standard deviation. It's the same test. Okay? So I'm going to have either sigma squared is equal to sigma squared naught, or sigma squared is not equal to sigma squared naught. Sigma squared is greater than or equal to sigma squared naught versus sigma squared is less than sigma squared naught. And then finally, I can have sigma squared is less than or equal to sigma squared naught, and sigma squared is greater than sigma squared naught. And so, again, the claim is going to tell me which one of the three sets I need to use. Okay, so first of all, we need to look at the claim and use the claim because the claim, again, has to be one of these hypotheses. Okay? So now, let's do an example. The math instructors are not only interested, in how their students do on exams on average, but how the exam scores vary. Too many instructors, the variance or standard deviation may be more important than the average. Suppose a math instructor believes that the standard deviation for his final exam is 5 points. One of his best students thinks otherwise. The student claims that the standard deviation is more than 5 points. If the student were to conduct a hypothesis test, what would the null and alternative hypotheses be? Well, he's claiming that the actual standard deviation is more than 5 points. Well, the claim here is that the standard deviation is more than 5 points. So this would be sigma is greater than sigma naught. Well, which one does this fit into? Right here. So then the way I would write the null and alternative hypotheses in this case is this. It would be sigma is greater than 5 versus sigma is less than or equal to 5. Does that make sense? So that's it. Okay? So now, oh, by the way, what type of tail test is this? Right, of course. Okay? That we should know. And so what critical value are we going to be looking for? Chi squared r. Okay? So just so you know. Okay, now, let's do a test. A scuba instructor wants to record the collective depths each of his students dives during their checkout. He is interested in how the depths vary, even though everyone should have been at the same depth. He believes that the standard deviation is 3 feet. His assistant thinks the standard deviation is less than 3 feet. If the instructor were to conduct a test, what would the null and alternative hypothesis be? Well, his assistant thinks that the standard deviation is less than 3 feet. He believes that it is 3 feet. So what's the null and alternative hypotheses? Well, it's going to be sigma is less than 3 versus sigma is greater than or equal to 3 feet, right? And so this is going to be a left-tailed test. And so our critical value that we're going to compare our test statistic to would be a chi squared L, just so you know, okay? Okay. Let's see here. So now let's do an actual test. Okay, so now that's a couple of practices of setting up the null and alternative hypotheses. So now we're going to do an actual test. And here it says, with individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times excuse me. Sorry. A post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoon is 7.2 minutes. The post office experiments with a single main waiting line and finds that for a random sample of 25 customers, the waiting times for the customers have a standard deviation of 3.5 minutes. With a significance level of 5%, test the claim that a single line causes lower variation among waiting times for customers. So shorter waiting times. Okay? So again, I'm going to read that again so you guys understand. With individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoon is 7.2 minutes. The post office experiments with a single main waiting line and finds that for a random sample of 25 customers, the waiting times for customers have had a standard deviation of 3.5 minutes. With a significance level of 5%, test the claim that a single line causes lower variation among waiting times for customers. Okay, so in other words, if you have a one main waiting line, the standard deviation for waiting times is less than if you have multiple lines with people waiting at multiple windows. So that's what we're going to test. We're going to test the claim that based on the sample data, that the sample, or that the actual standard deviation for waiting times is less than 7.2 minutes. Okay, so here's the information, and I'm going to write it over here just so we know. So we know that from the sample S equals 3.5 minutes. We also know that for normally distributed waiting times for customers on Friday afternoon, the standard deviation, sigma, is 7.2 minutes. And they took a random sample of 25 customers that were in one main waiting line. And they want to use an alpha level of 0.05. So the claim, so again, here's the claim. The claim is that the variation among waiting times for customers in one single line is less than what we have in multiple lines. So they're saying that sigma, right, is going to be less than what we normally have, which is 7.2 minutes. So that's the claim. So that means the null and alternative hypotheses are this. Sigma is less than 7.2 is the alternative, and the null is sigma is greater than or equal to 7.2. And so now the claim is, again, the alternative. And so now, what do we do now? Well, this is step one. And what's the test? It's going to be a left tail test. And then step two is assume the null is true. So we're going to assume that sigma is equal to 7.2 minutes. Okay. Now 3 is we're going to write down the information. So all of this that I wrote down is for 3. And then based on this, because we're using the sample standard deviation, and so this is going to be a chi-squared distribution. So what we're doing here is that we're going to have a chi-squared distribution with how many degrees of freedom? 24. So it's going to be a chi-squared distribution with degrees of freedom 24. Okay? So we know that the distribution of waiting times, or no, I'm sorry, the standard deviation, the distribution of S, right, is going to have a chi-squared distribution with 24 degrees of freedom. Okay, based on what we're looking at. We're looking at standard deviation, and it's a hypothesis about standard deviation. So now step 4 is our test. So now with the traditional method, we need to calculate our chi-squared star, which is going to be n minus 1 times s squared divided by chi-squared, or excuse me, I'm sorry, divided by sigma squared naught under the null. Okay. So now all we have to do is plug and chug, right? Because we know everything. So we know n minus 1 is 24. S is 3.5. So s squared is going to be 12.25, right? Yes. And this, we know sigma 7.2, so it's going to be 7.2 squared. And so our test statistic turns out to be what? So 24 times by 5.67. Okay, that's our test statistic. Now, all we need to know is our critical value. So in this case here, it's a left-tailed test, so we want the chi-squared L. And so we're going to use the table, and we're going to use the degrees of freedom of 24, right? And we're going to use alpha of 0.05 because it's a one-tailed test. So alpha is 0.05. So if I look on the table, I'm going to look up degrees of freedom is 24. And it's a chi-squared L. So we're going to use alpha of 0.05. So I'm going to look up 0.05 all the way down. And my critical value is 13.848. Okay. So now, I'm going to do my comparison now, right? It's a left-tailed test. So in this case, I'm going to reject if my chi-squared test statistic is less than or equal to my critical value. So here, chi-squared star is equal to 5.67. My chi-squared L is equal to 13.848. And is my chi-squared test statistic less than or equal to my critical value? Yes, it is. So therefore, what's the conclusion? Oh, I'm sorry, this is step 5. I'm sorry. Step 5 is the comparison. Step 6 is my result. Okay, so step 6, therefore, what do? We reject the null. That's it. So we reject the null, and then finally our final step is the conclusion. And so now we go back to the claim, and since we reject the null, there is strong evidence to support the claim. And so in this case here, we would say that at an alpha level of 0.05, there is strong evidence to support the claim that the standard deviation for the depths of, or what is it, what are we talking about? The waiting times. So at an alpha level of 0.05, we have strong evidence to support the claim that the standard deviation for the waiting times for these hold on a second, what is it? The waiting times for the post office, the people, the customers, okay? So let me repeat that again. I'm sorry, I'm getting a little scatterbrained. So we can say that at an alpha level of 0.05, we have strong evidence to support the claim that the standard deviation of waiting times for customers at this post office is shorter than 7.5 minutes using one single waiting line. That's what based on the sample data. Okay, and so that's the conclusion. Now, we can use the p-value method, and I'll show you how to do that. Now, with the p-value method, we still need to calculate chi-squared star, so there's no way around that. So when we do the calculation for chi-squared star, we're going to use that for our p-value. And since our p-value, in this case, is equal to the probability of being less than or equal to our test statistic. So it's going to be the probability that our test statistic, chi-squared star, is less than or equal to 5.67. And so now to find that probability, we're going to use chi-squared CDF on our calculator, and we're going to put in the lower bound, upper bound, and the degrees of freedom. Now in this case, what is the lower bound? Well, it's a chi-squared distribution. What's the minimum value you can have on a chi-squared distribution? 0. So since it's less than or equal to, the lowest value is going to be 0. And then the upper bound is just going to be the 5.67. And then finally, the degrees of freedom, which is 24. And so what is the p-value? Well, let's find out. So I'm going to go to my distribution menu. And I'm going to scroll down until I get to number 8, which is chi-squared CDF. And I'm going to put in 0, 5.67, 24. And I get 4.20 times 10 to the negative 5th power. So I get 4.20, right? Yep. 4.20 times 10 to the negative 5th power, which obviously you can change that to a decimal as 0.00004. And of course, we compare our p-value to alpha, and we're going to get the same result. P-value is equal to 0.00004, which is definitely less than alpha equal to 0.05. And so again, we reject the null and our conclusion stays the same. Okay? So that's how you do it. And those are the only 2 ways you can do this. Okay? Let me see here. Okay, so now, that's it. So that's where I'm going to stop. So that's doing a confidence test, or not confidence test, a hypothesis test for testing a single variance or a single standard deviation. Okay. So again, just practice some of these. Again, do some that have left tail tests, right tail tests, and two tail tests. Same process. Just make sure you use the correct critical value or you calculate the correct p-value. Okay? And next time we're going to start the 3 main chi-squared tests, the goodness of fit test, the test for independence, and test for homogeneity. Okay, until then, have a good night, and I'll talk to you later.